Coming to you live from the Science and Industry Showcase Theater in Rochester, New York. This is the second plenary session of the Frontiers in Optics and Laser Science Conference. Please welcome Laser Science General Co-Chair Randy Bartels.
Hello and welcome to plenary session number 2. We're at the midpoint of the conference and I hope everyone has had an extraordinary time this week. Finding knowledge and inspiration from technical talks, and mostly being able to reconnect with colleagues after being apart for way too long. To those in the theater and those who are joining online, we're glad you're here. Whenever I come to Frontiers in Optics and Laser Science, I'm struck by how much it feels like a homecoming. Walking through the convention center, I see a genuine breadth and depth of the community's professional interests and accomplishments. One of the responsibilities and joys of being a general chair is to invite the laser science plenary speaker. I and my co-chair, David Reese, were both in enthusiastic agreement that we would extend our invitation to Monika Ritsch-Marte. As a child, she loved science, but it was an open day at the University of Innsbruck that convinced Monika to study physics. She completed her degree in theoretical physics and received her PhD in quantum optics. Later, she became the chair in medical physics at the medical faculty of the very same institution that she had completed her first study of physics as an 18-year-old. And she's proud that her 2 daughters have followed in the footsteps of her parents and also gone into science. At the University of Innsbruck, her research transitioned to applied optics with a focus on laser applications and biomedical research. She's received numerous awards, but I'll just mention 2. So she has been awarded the exceptionally competitive ERC Advanced Grant called Catch It, and is essentially bringing Star Wars to microscopy to do tomography, my description, not Monika's. And she's a member of the German Academy of Sciences of Leopoldina, which is the oldest continuously existing academy of medicine and the natural sciences in the world. So biophotonics straddles the border of biology and physics, and it's given her the opportunity to work in 2 areas of interest across disciplines. In an interview, she expressed enthusiasm for emerging fields of interdisciplinary research. New questions cross boundaries, which create challenges in optics and also drive research. She said, "It is important to have passion for understanding how the world works and to strive to advance the science, to ask what will still be relevant in 50 years. And I think that encapsulates a lot of the work that Monika does. So, ladies and gentlemen, it is my great pleasure to welcome Monika Ritsch-Marte.
Hello, everyone, in the real life and in the virtual one. It's a truly great honor to be here and to present my plenary talk to you today. I would like to thank the organizers for this, and I would also like to thank the organizers for organizing yesterday's party, which has done a good job in relieving a bit of the tension before a plenary talk. It's been great, thank you. So, coming to my presentation. I would like to talk to you about wavefront shaping with liquid crystal SLMs, to look at the opportunities that arises for optical imaging as well as for optical imaging, as well as a little bit for optical trapping. What are spatial light modulators? In the most broad sense, spatial light modulators can mean several types of devices. One could think of deformable mirrors, where we have a membrane being actuated, or one could think of tiny micromirrors that can flicker between an on and off state, the digital micromirror devices. And then the thing I will talk about are the liquid crystal SLMs. Now, these 3 types of devices, they each have their pros and cons. For example, as you might already know, for the deformable mirrors, they have very large phase stroke. It could be like easily 50 times the 2 pi, but then they tend to have fewer actuators than other things. On the other hand, the digital micromirror devices, they're very fast to operate. So if you have the speed, then that's a good thing to go for. On the other hand, they're only binary, so you can have an on and off. So that's kind of disadvantage, as I will show you. The liquid crystal devices are probably the most flexible one. It's safe to say that. We have a lot of pixels. Unfortunately, they are a bit slow. So let's focus on the liquid crystal devices, the LCOS SLMs. They are crystals. If you look at the liquid crystals which have a certain direction, a preferred direction, and if you apply a voltage to a pixel like that and come in with a certain linear polarization, then you have something that, an effect that the refractive index in that pixel changes, and you have a pre-calculatable phase delay. It's not linear, but it's a known response, so you know exactly what voltage you need to create a certain phase delay in the pixel by applying the voltage. Now, typically, as I said, they have a large number of pixels. 2000 times 1000 is a very common display resolution, but it could be also more or less. And this, as I will discuss, is important for space bandwidth product will have an impact on what kind of things you can or cannot do, like things like multiplexing, for example. Pixel size is typically in the range 10 to 20 micrometers. It could be a little bit less, a little bit more, depends. And this, of course, is important for the maximal diffraction angle that you can actually achieve. And then fill factors are quite high nowadays. They could be more than 90% of effective things without the gaps in between the electronics. But the refresh rate is not that high. It's several tenths of hertz, so 60 hertz typically. And another thing that is common, that they work in reflection. It's usually not shown in the schematic diagrams, but most of them work in reflection. And that means sometimes it's a bit bulky in the optical setup, often not shown. Now, my group in Innsbruck has more than 20 years of experience in working with these liquid crystal displays. We use them for all kinds of applications. We started up in buying our first SLM for doing holographic optical tweezers. This is something that's been very highly successful, so you can create multiple traps and you can move them around in all 3 directions. Has been pioneered by people like David Griever, Helena Rubinstein-Dunlop, or Miles Patchett. And then we've been doing things like beam shaping, of course. You can do, we're the home of the holographic Edelweiss shown here. So we do all sorts of vector beam creation, simulation and experiment, but we've also been using it for beam delivery. For example, if you want to meet the phase matching condition, if you do coherent Raman, like cars, imaging in wide field mode, then you need to have precise and controllable beam delivery. Moreover, as I will show you, we can also use them to advance microscopy and optical imaging. That's something I will talk about in detail. We use them routinely. We can do multiplexing tricks to do several things at the same time with one and the same hologram. Or we can also do aberration correction and adaptive optics. Now in my talk, I will have 2 parts. I will have a longer and more general part, which will rely on these 2 things, on the programmable microscopy and on the multiplexing that one can do in this holographic approach. And then the second part is on more recent work, and that will show you some frontier work on how to advance the depths of brain or tissue imaging using adaptive optics and wavefront shaping ideas. Now let me start with the programmable microscope. Well, I could tell you now that we had this SLMs bought for optical trapping, and then we thought, oh, wouldn't it be great to also do something like programmable microscopy or customizable microscopy? And then we started doing this, and at the time, it wasn't so common to use SLMs for this sort of thing. Now they're everywhere. But actually, that would be fake news, because as it happened, my colleague Stefan Bernet, who also made the jump from doing quantum optics to doing applied optics at the same time. So together we founded this lab. He did the habilitation in experimental quantum optics, me in theoretical. He worked with Anton Zeilinger, I worked with Peter Zoller. And one day we had the following problem. We came into the lab and our trapping laser was busted. It was gone, it died overnight. So we had a microscope and we had the SLM. And we thought, why can't we just try doing something just with these two things? And we started thinking about doing Fourier things where we put the SLM and do a Fourier filtering that is programmable. That was the birth, so to speak, of how we got interested in advancing imaging with SLMs. Already quite a long time ago. We've written up a review on these early things that you can look up here. So this is just schematically what we do. We have partially coherent light. We're looking, that's where the sample sits. We have an inverted microscope, the objective that's here. We guide the light with some relay telescope lenses to fill the SLM, and then we do a programmable Fourier filtering. So we're looking at the light with a blaze grating. We do off-axis. We look at the camera here, and this is just changing what we put on the SLM here. The appearance changes completely. We go to something that's totally transparent because it's an unstained cheek sample like here. And then we can do dark field or bright field by just knocking out different Fourier components digitally on the SLM. So we can do a contrast modulation by changing the images that we have on the SLM. And just a few words more on how we do this. So here would be a kind of a Wernicke phase contrast where the phase ring is here in the middle. And you can see in a real phase contrast microscope, it has to be, in a real phase contrast microscope, the items have to be, you have to know what kind of samples you're looking at, what to expect. How much contrast can you get if you need a certain attenuation to get a good interference modulation contrast. So you have to anticipate that. We can really customize that by changing the pattern that we put there. We can then say how much we actually want to have this absorptive in a way by emitting the phase grating. We do not get any signal from there towards the camera, so we can adjust all these things that need a hardware components normally. And just a word on the light sources that one typically uses. So we have partially coherent light that we're using here, either by having a rotating diffuser. We can adjust that to not have enough speckle noise, but still have enough of the effect, in the interference effect, and or we use LEDs. So but we can also do shearing interferometry, where you have incoherent light, totally incoherent light, which is split by the SLM, not by hardware, Wollaston prisms and recombined. And in this way, it's also doable to do complete differential interference contrast, customizable, and with single shot, you can get the quantitative DIC with this method. So this was the earliest things that we did. Now, we can also invent new types of microscopy, and this is an example here for putting in a point spread function which has a helical phase front, a helical phase profile, a phase vortex. And you see, if we do this, we get something which we named spiral phase contrast, because actually it does a kind of a two-dimensional Hilbert transform, can also be done in post-processing if you just take the image and then do a post-processing. But we're doing it here as an optical processing, and we see that here you see nothing on the human chromosomes, but if you do this spiral phase contrast, all the contours, the edges with something, either the refractive index or the intensity changes, you get an enhancement of the edges, and it shows up really, really well. So there's semiconductor surfaces or human or biological samples that we have here. Now, talking about computer-generated or synthetic holography with SLMs, just let me remind you very quickly about the idea. You know, of course, holography makes use of the fact that the phase information of the light coming from an object is stored in the hologram that you do in the writing phase, in the recording phase here. And then later, when you look at the hologram that you have written, that you've recorded, with the same reference beam, you generate light that it generates an appearance, a wavefront, that as if the object would be over here. Now, of course, you can extend this to think, okay, I can simulate an object, a sphere or something else, and I know what the scattered wavefront will look like. And then you can pre-calculate that and have that faceplate etched. And it also would look like something that appears from here. And then, why should we etch it or make a hardware hologram if we could do something with an SLM where we can actually change what kind of scattered field we add with the field, with the reference beam, that we use whatever we have assumed in the calculation. So we can do something where we have a totally computer-generated attitude. There isn't a hardware component that corresponds to hologram to be viewed, but it is all the SLM that does that. And I like to look at this picture here as an example of strengths and the weaknesses of this. This is a famous image, work of art by Maurits Escher, who is an artist from the Netherlands who liked to play with perspective in 2D and 3D. So there are stairs that go up and down and are impossible to exist in real life. And this is something, for example, that one can create with an SLM. So as a projection at a certain distance. Let us look at a simple and very popular algorithm, because it's very short, that will calculate the pattern that you have to put on the SLM to reconstruct this image by Maurits Escher at a certain distance. And basically, I guess most of you know it, it's a very simple and therefore very popular algorithm. It's basically going back and forth with Fourier transforms going to the far field and backwards, inverse Fourier transfers. You start with a random phase, and then you start with a random phase, and then keep the phase, replace the amplitude with constant illumination or a Gaussian or whatever you want to do. You do the inverse Fourier transform, you keep the phase again to replace with the intensity that you want, and then you do a couple of times, like 20 iterations, until it converges to a certain limit that you can set. Interestingly, in this example that I did for a lecture, actually, the symbol I use here matches a lot the new Optical logo. I noticed that yesterday on the party. I talked to Gerd Leux, who had this tie. I said, oh, you have to send this quickly to me. I have to show. But this is exactly without me knowing it. This is very old, actually. But it does look a bit like the new Optica design. So. Now, here we have a simulation. I hope it works. Not really. I'll try again. This is now, should be looping. It doesn't work, unfortunately. I tried it out before, but it doesn't work. So I should show you the convergence. This is in between an early, pretty early stage of the algorithm. It gets a pretty good and well-contrasted picture in the end. Don't know why it's not working now. Try again. Oh yeah, now we have it. It's toggling very fast between early stage and the final stage. There's 100 iterations that you can do. So you could think, okay, fine, I can do that. I can reconstruct any picture I want with a simple algorithm at a certain distance by adding a certain lens term. You can define where you have to put the camera or the screen to capture it. But then, if you look more closely, you see that actually it's not so nice if you look it up close. So there are some problems with this, and especially if this was calculated with a bit more data points. If you do this in the real life with a laser to illuminate in the experiment, you would have a lot of speckle appearing from there. Now, I thought in my talk, what could be a good thing to present? I thought maybe we think ourselves often, what kind of SLM should I buy? What features should I have for a certain application? And we do get asked that question also quite a few times by people who know that we have a lot of SLMs from different companies and of different function. So people ask us, what should we do? And in this sense, I thought it would be maybe nice to go through these with a lot of examples from the past years, 20 years of experience, by asking dumb questions. So the first dumb questions that should follow up on what I just said before would be, what are the limitations caused by phase-only modulation? We have phase-only modulation. Is that the reason why the result wasn't really, it was so-so, but it wasn't great? So what comes from actually from the fact we're doing phase-only modulation? Let's look at that. So in the simulation, we have used a crude algorithm. We have used just a Fourier transform as for the propagation field, which is not physically the perfect thing. We have used random initialization, which stayed with us for a while. Better algorithms are available, stochastic gradient descent and such. You can make it a bit better. But on the other hand, in the experiment, you will still have speckle if you go to coherent fields. And in real life, there are many more physical influences like aberrations on the optical components and the SLM itself, which has quite often some astigmatism, for example. We have fringing fields, a crosstalk, and all the other things. So we really need to include the captured images in iterative search, which we do, for example, if we do quantitative measurements of optical force and torque. And I realized that people do that nowadays in the amazing, I don't know why it stops every now and then, in the amazing session on Monday on near-eye holographic displays. It was amazing, the progress that's been made the last 2 years. And people use this camera and in combination with neural networks to improve these algorithms. And it's called neural holography. It was several presentations with camera in the loop training. Quite amazing what you can do there. So certainly the algorithm is part of the problem here. But what is the part of the phase? Now here, that is just a normal imaging setup. We have the SLM here, a lens, or could be a lens term added there, and we'll look at the spot that we're creating on the screen. Now, if we add a blaze grating, we displace the spot a little bit. Now the question is, if we want to do the next the next hardest thing and have, instead of one spot, we have 2 spots that we would like to form, then the ideal thing would look like this. If you take the 2 spots there and you propagate them physically back to the plane where the SLM sits, you would have a real wavefront. You would have to modulate the phase and the amplitude there. But you can't do that because the SLM actually only does it only does the phase. So we should do this, but we're doing that. So should do this, but doing that. And now if we do that, you see, that's what people call ghost images or ghost traps. So in object trapping, because of this phase only, you do get artifacts. And these are they're weaker, but they're always there. If you characterize everything well, you know where they are, you can deal with it. But you have to be aware of the fact. So that's one thing. Can one shape a real wavefront? Well, one can shape a real wavefront nevertheless with phase only. That's an example that we have here, where we're looking at a rabbit and an eagle that we're creating in 2 different planes. That was done with a multi-plane Gertz-Saxon for a public outreach thing. And interestingly, on Monday, everyone showed rabbits in this AR/VR hologram. I don't know where it comes from. If somebody could tell me why they're using the rabbit, I know where we're using the rabbits. Because for the kiddies, it was kind of nice to have the Tyrolean eagle up there in the sky and something down to earth, and we chose the rabbit. So that's why. There are other ways to do this. Either you do a multi-plane algorithm, which optimizes 2 planes in the Go, or if you do this is, I would call a 2.5D, so it's 2 planes only, but the in-between is not really addressed. But you can do real 3D operation by going to a double SLM technique. Some people call it also double phase. So you use the SLM twice. Once to form the Fourier transform of what you want in intensity, and then you fix the phase in a second step because the phase was not right. But this, as you see, can be quite bulky. You can use a 1 SLM for cost reasons and have often the aspect ratio 2:1, so that's doable. But obviously, these lengths are very long, and you have to fold back, so the setup gets a bit complicated. The next question, how about efficiency? And are more phase levels better? Well, the efficiency The efficiency, for example, you have to, for example, in this blaze grading setup, it's an old holography trick, off-axis approach, you add a blaze grading, and then you get rid of the undiffracted light, which could give you a blur, not a blur, a blaze, a contrast deterioration in the middle. So off-axis, you'd like to know what the diffraction efficiency. Now, theoretically, a perfect blaze grading would give you 100%. It would be very nice to hit all you want in the first diffraction, first order diffraction. But, so that would be shown here. So if you have a perfect blaze grading, then the sinc function here would predict that you would have 100% diffraction efficiency. In real life, you don't have a real blaze grading, you have these phase steps. So you see, if it's not perfect, if it's just binary, a binary phase hologram, only 0 and pi can be done, then you see you're at 40% theoretically. So that is a big difference. On the other hand, if you're looking at phase steps at 8-bit, it's already pretty good, the sinc function. So not necessarily do you have ultra many steps to get a good theoretical diffraction efficiency. However, on top of this, we have what people call the light utilization efficiency. And this light utilization efficiency is all the extra things that come from the device, from the physics. So there you have 60 to 90%, depending on whether it's refractive and has an anti-reflection coating, and although it's like fill factor losses from the electronics, scattering to the side, and the electronics and all these things. So that is on top of the theoretical thing that you have. Now, are liquid crystal SLMs too slow? I myself complained about this already. So here you can see something where we run it differently. For example, Gregor Thalhammer had the idea, maybe we operate the same hardware that we have, but do it a bit differently in the algorithm, what we do. And you've just been very good in speeding up the holograms 10 times and make it also a bit truer. And the only thing you have to have is an internal refresh rate that is large and more than 2 pi phase stroke. So here you see again a time trace of if you do this trick, we called it Overdrive Plus, and it's actually, it was implemented in one of the Meadowlark systems that they call this Overdrive system. Came from Gregor Thalhammer's idea, and we studied it with Miles Paget and Gordon Love and Richard Bowman, who happened to be in Innsbruck at the time when we did this. So you see, we have a much faster response. We need to close up to see how it's switching, and also it's much truer in what you actually have in terms of phase shift if you measure it out. So the trick there is to do two things at the same time. First, if you go for speed, you overdrive. You don't go to a saturation level here. If you want to go there, you overshoot and come down, because the coming down is usually faster. So you overdrive and quickly settle into what you want. And then the other thing is you do a different rounding operation. If you have to go from 0.9 times 2 pi to 0.12 pi, it is a long way. But if you have more than 2 pi phase shift, you could as well go to 1.1 2 pi to have the same, because it's only modular 2 pi. So with this different rounding implemented in the control of the SLM and the overdrive, we were able to speed it up 10 times. Now, are more SLM pixels better? Here I would say, yeah, for certain things, certainly yes. For example, we have been looking into depth of field multiplexing. So by multiplexing, I mean, I'll take the images is broken up into several sub-images which contain different information. In this case, we're creating a hologram that looks at different false colors depths and puts it in different locations here on the SLM. And this can be done by coming out with the appropriately calculated hologram. And basically, it means that we have a point spread function which has several lobes and can simultaneously look into different layers, so of a sample. And here you see that we can do dynamic streaming scene without losing anything in this dynamic and fast level, because we're looking at slices, in optical slices, truly simultaneously on one and the same camera exposure. And of course, the resolution sacrifice maybe a bit of resolution, but the resolution is, and the optical sectioning is dictated by the optics that you use, so by the hardware NA that you're using for the imaging. I skipped this, won't mention it. You can use chromatic effects to an RGB illumination to triple the number of planes that you can look into. Or maybe come to this. Multiplexing different modalities is also possible. Let's say we do a phase contrast here and a spiral phase contrast there, or dark field, bright field, and we all have the different contrast modalities and the same camera exposure, meaning it's absolutely simultaneously in changing objects, so you truly have the same modalities at the same time. And then there's a trade-off, of course, between field of view and resolution here. We have the space bandwidth product is fixed, and we have to sort of decide what we want there. You can display many other things. You can multiplex many other things, like vector beams. Andrew Forbes here has done similar things for vector beam multiplexing. Or you can also do, for example, multiplex between doing optical trapping and optical imaging at the same time with the same hologram. What is this, the thing I said about the space bandwidth product? Now, if you want to do multiplexing into individual parts on the image, of course, these images have to be separated. So if we're looking at the zero order image and has an angular spread, and then we need to know the diffracted image, it has to carries the information from the other sub-image, they have to be separated, so they don't overlap. Now, if we're looking at the information content in the image plane, where we use the field of view in units of point spread function for coherent illumination, then we find this expression here. It has to be the same as the information contact in the SLM plane, where we're looking at the used panel diameter in units of the point spread function of the lens. And then we apply the finest possible grating, that's a 2-pixel periodicity, and if we plug that in, that we find that this information content scales with the number of pixels. So if you want to do multiplexing, then of course, have a given pixel size, delta, then it pays off if you have a lot of actuators, a lot of pixels in the liquid crystal display. So that's the reason why for this sort of thing, you really need to have a good display resolution. Otherwise, you not able to do this efficiently. How about color dispersion? Well, color dispersion is seen here as a negative bi effect that you have and try to avoid. If you have different colors, then the refractive index of the liquid crystal depends, of course, on the wavelengths. But you can also turn it around and say, what are the opportunities that come from this color dispersion that we have? Can we utilize the color there? And one and the same voltage pattern can be read out by 3 different illuminating colors in a very different way. You know? What could means 0.3 times 2 pi for a red one could be, I don't know, completely different value for up to 7 and more, 2 pi in the blue. So we're utilizing this by trying to come up with a hologram that sort of does 3 tasks equally well. I mean, there are compromises if you're trying to get 3 different tasks at the same time. But with this, we've been able to do something, and that's quite a long time ago. I've seen Rubik cubes around also on Monday a lot. And this is just a simple Gertzberg-Saxton with a 3-fold illumination, RGB. And you see that this specular appearance could be improved by better algorithms, more modern algorithms. But it's possible to do these things, read out one and the same hologram at 3 colors, and combine it to give you the color image that we have here, a color hologram. How does it work? Well, it works in following way. Here you have the phase shift for one wavelength, and for the green, and the phase shift for in the near infrared or red, and then you calculate your hologram, you know what this is for 2 colors now, you know what the phase shift should be for the green, and you know what the phase shift optimally should be for the other one. But then it would be a complete surprise if that would work out for all the pixels and all the phase shifts that you need. So obviously not. But then you realize that you can add multiples of 2 pi's. And this is the line that the SLM actually can do. And there will always be one point if you're adding a number of doable 2 pi phase shifts, that we have one where it's actually not too far away from the line where you can actually have a physical effect in the SLM. And this we have used to shape the in fluorescence microscopy, to shape the fluorescence excitation light and in the blue and the green fluorescent emission line at the same time with one hologram. So we're shifting in the blue, we're looking we form 2 spots where we're looking that are just in front, before and after the focal plane. And then in the green, we do something that actually undoes the shift axially and puts it side by side. So that's doable, meaning that we have simultaneous acquisition of 2 different settings for confocal. And if you compare with the confocal image that is sequentially obtained, there is almost no difference. So it can be used to parallel confocal, speed it up a bit. Now this is an example here where we have not too visible, but the near infrared doing optical trapping. And the visible does a spiral phase contrast. You see there's the edge enhancement in the spiral images, and then we can move them around at the same time under full control. How about polarization? That's just a thing I'd like to mention because it's kind of getting into fashion again. They look at the polarization here, and it's kind of a nostalgic thing. That was a long time ago in 2004. We did optoacoustic holography, and we used an SLM in combination with a polarizing filter here. So we have an amplitude modulation. If we turn around the input polarization, we come in at the wrong one. We rotate the polarization with an EOM, and then you can have an amplitude modulation. If you do that at megahertz, you can create an optoacoustic field and create something like an optoacoustically generated Bessel beam or donut beam or something like that in the aquarium here. I just wanted to show you how old these things and what PowerPoint looked like in those days. It was not very convenient at the time. Okay, so the last thing I'd like to cover here on the questions before I move to the next topic, which will be much shorter. How sure are you that you actually get what you want? It's a very broadly asked question, but I mean it in a very specific way. So you do your calculation, you have the best possible algorithm, you hope that the light will be put into the right places, but you never know, because there are actually a lot of things at work. And one of the really important thing is the so-called fringing fields, or pixel crosstalk, which started to be one of the most severe limitations for us, especially when we do quantitative force measurements and quantitative torque measurements and such things, in optical trapping, with quantitative numbers out. This fringing field effect here, there contribute 2 mechanisms. There is a smoothing of the electrical field patterns compared to the voltage at the electrodes, so it's not quite as sharp anymore, the features. And then there is, of course, elastic interaction at the boundaries between the pixels, between the molecules of the LC layer. So these 2 things, they both matter. And so here we measured these things, and you look at what you ideally expect and what you really have, and you see it can be quite large. You know, this is the first order diffraction where, for one case, it depends a little bit on the orientation of the molecules in the fabrication. If you put your grading on this parallel or orthogonal to this preferred direction of your liquid crystal from the manufacturing, it's a big difference here. It's not too bad for the first line, which is important for the Blaze grading, for the off-axis holography. But if you look at the 0 order here, dashed line with theoretical prediction, blue line, what you really have, or also on the higher orders, it can be very bad in some cases. So we did a full, I'm just flashing it, it was horrible, it was Simon Moser's master's thesis, a very bright guy, does a PhD now with us. He calculated all this funk on-scene free energy density things to really get quantitative number out, to compare it. And then you see that our the simulations and the experiments for our SLM really on top of each other. But of course, you can't do this if you want to characterize your given SLM. So we came up with an idea to have a simple and doable approximation where you need to do a fit. It's like exponentials and polynomials of exponentials, and it has a slight asymmetry, and it gives you a pretty good correction already. And this now completes the first part of my talk, and very quickly I'd like to go over to this was more backwards looking, explaining some limitations and some good things about SLMs in the past. And this is my team. These are the major players here. These are the guys, when I say as a theoretician, oh, it would be so cool to do this or that, the experimentalists bring me down to the ground and say, well, maybe not with our instrumentation, maybe never. So I have really great people here. If we were in Innsbruck, such a nice city, I think there would have been professors somewhere else already, all of them. Now, the next topic here, and it's going to be shorter, as I said, is the wavefront shaping for diffuse tissues. That, of course, is very challenging. So basically, what we want to do here is the following. We want to do, so we go from here, where you have coming with some specific nicely shaped beam, but then you have this aberrations on the slow scale induced by the tissue, or even worse, if it's not just smooth aberration, but really multiple scattering, that will happen, this will happen. And we want to guess the phase that we put there to actually have it corrected. So that is the thing one would like to do. And this all started really with this famous Velikopo-Most paper. It's a really interesting and high-level topic at the moment. And a lot of people are looking into pushing the limits from biomedical imaging into the depths in scattering tissue. So here are various things like high penetration depths are the medical imaging modalities like X-ray, MRI, ultrasound, and so. Compared to optics, this is all much deeper. Optics, we're talking millimeters and below, whereas here we can have a high penetration depth, but of course the resolution is much better in optics. So nonlinear scanning microscopy, where you use two-photon excitation, is something we can penetrate further into the tissue with reduced scattering and absorption. And people are making a big effort at the moment to actually do adaptive optics to enhance this depth a little further. There is a nice recent review where this roadmap on wavefront shaping and deep imaging, which I really recommend you, 23 articles show you the state of the art. Adaptive optics and multiphoton excitation frequency, basically the idea is if you go in with, and you do nothing, what will happen here if you want to excite a spot and interrogate whether there is a fluorescence for a molecule sitting there or not, you're not really successful. We're actually exciting, putting the light all over the place. So we need an engineered wavefront, and of course the art is to know what to put there. That puts a nice spot there. The beauty of this is, of course, the light will be aberrated on the way out. You don't care. As long as you see you hit something, that's good. You don't care. If it's not too diffuse that you don't get a signal, you don't care. Now, the question is, of course, what do we have to put there to achieve this? And there are direct and indirect or sensorless methods that have been developed. You can either directly measure with a Schack-Haltmann sensor or something like that. You measure it, and then you know what you have to do. Things from atmospheric research, where adaptive optics was a field where it first started, know this very well. But then, on the other hand, it's better to, or it's sometimes also good that you don't have to measure, because you need, for the direct wavefront sensing, you need a guide star. You have to look. You have to know something like a star. There should be a point, and then you're looking what you have to do to make it a point. So here, you need something we know it should look like to make this work, whereas here, you're trying to iteratively guess. You do something on the wavefront, you look, is it getting better or not, but you're not actually measuring the wavefront, you're trying to guess it, and it doesn't need a guide star. So all of these two methods, they work. but have their pros and cons, being in terms of speed and other complications. Now, don't want to go into much detail, but there are two very popular methods for indirect wavefront methods where you want to guess iteratively, and they are variants of each other. Here we have a static reference, and we are changing on the SLM, we're changing some pixels with increasing number of frequencies we excited, and then we analyze in a 1D FFT the time trace to get, and then you know where you find the phases, how to extract them, to put them on the next iteration as a correction. Whereas here in F-sharp, we have a galvo and a static reference beam, and the galvo changes the position, but also can do phase stepping. So from the intensity image, we get the phase out by taking 3 phase step images, and then we do a 2D FFT of the data and get the next iteration phase mask out. And we have recently, well, this is actually work, the wavefront shaping. The lead PI is Alexander Jesacher, so I'm just reporting more or less. He is the boss on this project. And Molly May was is a really talented postdoc, was in Innsbruck for a while. Now she's back to Boulder, working for a big company, but doing still research. And so they are the lead people on this. They came up with a great idea how to improve the speed of these things for a variant of S-sharp. And she called it Dash. You know probably from The Incredibles, Dash is the very fast guy. So it's called direct adaptive scattering compensation holography. And basically it's a simple trick. You can implement it with the same hardware. You just have to you correct at more often. So you do the updates very, very often, not after a full iteration, but you continuously update. And the other change is that you take the angle, the phase, not just over the corrected beam, but you include the test modes. There could be pictures like people do sometimes Hadamard or Zernike. In our case, it was tilted plane waves. So if you do these 2 changes, you get something that converges very fast. Now here's a comparison we did in simulation for F-sharp impact, which give same results, because we showed in the appendix that they're actually variants of the same thing. So F-sharp and impact go up here to the same level that we have here for the dash. Dash is in blue, and these are other popular methods. This is for the high signal-to-noise ratio. If there's not a lot of noise, then all these things work pretty well. In a medium signal-to-noise regime, this starts to be a little bit worse. And now ours is, for low signal-to-noise ratio, only dash converged. So it's really been a step forward in a way. You can also look at how many photons are required to achieve the 50% correction. And then you find that dash needs about half as many photons. But on the other hand, how long does it take to achieve a 50% correction? And also here we see this is modulating various types of SLMs. They're not the fastest, but it's the things we have access to. So it requires less time, and that gives a very quick, reasonable correction. And it actually is the correction due to the instantaneous updating all the time. Even after 1 iteration, you find something that's already pretty good. So these are fluorescent beads under scattering tape, and you can see that just 1 iteration and you already have improved quite a lot. Other methods have to wait a bit longer, do more iterations to get there. This is into mouse brain at the 530 micrometer depth. That's a really pretty high depth. 0.5 millimeter in is not nothing in mouse brain tissue. And final channels is always a challenge in optics. You'd like to have all the information. You do not want just to look in a super highly resolved matter in one spot in the brain or in the tissue or in the organ. Then you would know everything about nothing, yeah? It's a tiny spot, you know everything about that. But about the biological understanding, that doesn't help. You'd really have to look at various spots at the same time and be able to adjust and pick those spots where regions of interest. And this we have been doing now. We have changing this to simultaneous correction at multiple points by putting the SLM now in a sample conjugate plane, not in a Fourier plane, because in the Fourier plane you would not be able to address spots. It would just be a phase change. So you have to put it in a sample conjugate plane and you can move things to a different spot. And we do the correction of this for the multiple spots, not so many, 7, 10 maybe. And you can see now these are microglia with expressed GFP. This is without doing the trick, and with the trick, at least you have several windows now, not just one into the sample. So live cell imaging is very highly critical. It's very difficult to do. And this is a comparison. You see fixed tissue, that's where you put chemicals on, and your refractive index becomes much more homogeneous, and the things are dead, they don't move anymore, they don't fluctuate. There it's simple to do, but these are results from really live imaging. Acute slices, as the biologists say, that are cut in the lab and we're still alive and we're just doing it. It's very demanding, we're still working on it. So in conclusion, we have a new robust operation method. It's a variant of F-sharp. Has fast convergence, even after a few steps. We're pretty good there. It has good photon efficiency, and we can do multi-spot corrections. And with this, I'd like to thank also the group doing this in Innsbruck, together with, this is the boss from our physiology institute. They are interested in studying the physiology of pain, so we're hoping to do some real biological questions that we can answer with this. We just started the collaboration a few months or almost a year ago, so looking forward to have some real biological questions. And now I'm at the end, and I would like to advertise a postdoc position that is available. You know, this is a picture taken from Innsbruck, and now it's hard to beat, right? That's what he said yesterday in the plenary. Austria is hard to beat in terms of beauty. So Germany, Italy, and here we have our institute sitting down there, and we have the guy here. Could be me. It isn't actually, but it could be. And then maybe it could be you. So people who are interested in skiing outdoors and have a good combination of visiting other labs in Europe is all nearby. We're at the crossroads in Europe in a way. And so please send me an email. I'd be interested. I thank you for your attention.
All right, well, thank you, Monika, for a fabulous talk, and I'm always impressed by the great breadth of creative ideas that your group does and pulls off.